Okay, so here in this part here we will be looking at damp vibrations, the damp vibrations. Okay, so here in this part here I'm going to tell you what are the different types of vibrations that we'll be looking at. But we only look at the first two types. We are not looking at force vibrations. Okay, we are not looking at force vibration for any diploma levels. Now the types of vibratory motions. So the first one is your free or natural vibrations that we have done earlier. That is your longitudinal vibrations, your transverse vibration, your torsional vibrations, okay, and more. Okay, you have longitudinal, transverse, and torsional. Okay, no external force acts on the body for any free or natural vibrations. Okay, so there will be no frictional force due to surrounding air. That means we neglect the frictional force due to the surrounding air for this case. Then after given an initial displacement to any masses, it will begin to oscillate naturally. Okay, naturally, okay, without any external resistance or resistivity force acting on the oscillating object for any free vibrations or natural vibrations. Then the next, the frequency of the vibrations, usually we call it as the natural frequency or the natural circular frequency. So here, given you the graph of the elevation against the displacement graph here, where you have the crest, trough, amplitude, wavelength, and so. Okay, so this curve here or this graph here is actually referring to the natural vibrations. That's what we have done. That's what we have done for the springs and the pendulum. Please, we have to neglect any external force that is going against the vibratory motion for this case. So the next one is the damped vibrations. So there is a reduction in amplitude. Now in the previous case, there is no reduction in the amplitude. So the amplitude for the case always remains constant. Always remains constant. So as you can see here, okay, the amplitude that we measure from the X to the crest or to the trough of the curve is called the amplitude. So the amplitude for each of these successive oscillations are the same. So you can see the distance, vertical distance from the x-axis to the trough or to the crest is the same. That is the amplitude. So constant. The amplitude is constant for any natural vibrations. But for damped vibrations, the amplitude of the vibrations, okay, reduces over every cycle of the vibratory motion, the vibration. Next point, the motion is said to be damped vibrations. It's just like your shock absorber, okay, absorbers and your door closer. These are very good examples of damped vibrations. So due to the fact that a certain amount of energy possessed by the vibrating systems, all vibrating systems, they can consist of kinetic energy. Okay, they have kinetic energy, and this kinetic energy will die off slowly. Okay, and is always dissipated in overcoming frictional resistance to motion. Now, this kinetic energy of the vibratory mass or the object, okay, the energy losses due to the surrounding air. That means you have energy conversion. That means kinetic energy to heat energy due to the surrounding air, due to friction. Okay. So this is an example what you have, the graph for any damped vibrations. Okay, for damped vibrations. Okay, and damped vibrations, okay, is separated into three different cases. Damped vibrations is separated into three different cases, which we call it as over-damped, critical damped, and underdamped. Okay, we will go into each of these later on. Okay, the damped vibrations, the three different cases in the section 5.2. In section 5.2. Okay. Now force vibration. Now we are not going to do force vibration. Now the body vibrates under the influence of any external force. The body is said to be under forced vibrations. External force applied to the body is a periodic disturbing force created by unbalanced force. Okay, so I have a short notes over that, so we can just take a note. Okay, when the frequency of external force is the same as that of the natural vibration, resonance takes place. Okay, so we will go into that later on when you are doing your degree. Okay, so this is a system where you have for a damped vibrations. So you can see, okay, you can see there is a spring here. You have a spring. You have the spring. You have the spring. Okay, that is a spring. Okay, with stiffness S. We use stiffness symbol for stiffness of spring here as S. And then this is the dashpot or the absorber. Okay, and you have the mass here. So basically you have three of these components for damped vibrations. Now motion of a body is motion of a body is resisted by frictional forces. You all know what are frictional forces, right? Okay, in vibrating system, the effect of friction is referred to as damping. The damping. It's just like, for example, you are driving a car and it goes over, okay, a hole, okay, on the road, or the middle of the road. Let's say, for example, okay, and it creates vibrations. Okay, when you drive the car over the hump or the hole, okay, it gives vibrations. So what is the use of a shock absorber? Is to reduce, to absorb the energy caused by the shock. Okay. Now the damping provided by fluid resistance. So usually when you refer to the piston and cylinder device for the damper or for the shock absorber, for the damper usually called. Okay. Now the damping is provided by the fluid that is in the cylinder. Okay, fluid. It's just like where, for example, when you refer to the door closer, maybe inside of the cylinder, you have something we call the hydraulic fluid. Okay, we have hydraulic fluid. Okay, so any motions between the cylinder, between the pistons, the pistons that is within the cylinder, will cause frictional force, will induce a certain amount of frictional resistance. This will cause, okay, the vibratory motion to be cut off. That means shortened or being absorbed. Now in damped vibrations, the amplitude of the resulting vibrations will gradually diminishes. Okay. So as you can see here, or I have shown you earlier for this. Okay, this here. Now this is due to the reason that a certain amount of energy is always dissipated to overcome the frictional resistance. You can refer back to your YouTube if any one of your English is not so good. Okay, you can refer back to your YouTube. Okay, you can refer to the subtitles. Okay. Now, the resistance to the motion of the body is provided partly by the medium in which the vibration takes place, and partly by the internal friction, and in some cases partly by a dashboard or other external damping device. Okay, so as you can see here, it actually, when the mass vertically, that means being lowered down vertically, so you have the spring extends, the pistons that is inside the cylinder of the damper will move downwards. So both will cause a restoring force actually. For the dashboard, you will have what we call damping force. For the spring, we have what we call a spring force or a restoring force. For the mass, we have what we call the inertia force, that is MA. Okay, so you know what is restoring force, right? So that is the stiffness of spring multiplied by the deformation of the spring. It is extension or contraction. And then for the damping force, okay, for the damper or for the dashboard, we have damping force is equals to the damping coefficient, which is written as C. Later on, it will be defined, each of the symbol, and then multiplied by the velocity of the piston that is within the cylinder. Okay, and then for the mass, you have the inertia force. So according to Newton's second law, inertia force is equals to the product of mass and acceleration. So when the mass moves downwards, that means when the motion of the mass is downwards, okay, so you will have an inertial force of mass that is acting downwards. For spring, when you look into this case, it is being extended, elongated. So you have a restoring force of Kx, which is acting upwards. Okay, and the damper or the damping device, when the pistons move downwards, there will be a restoring force of the damper or the damping force, which is acting opposite to the motion of the mass. So the mass is moving downwards. The force that is acting, the damping force that is acting on the damper will be facing or moving upwards, will be acting upwards, sorry. A better word says acting upwards. So you have both forces acting upwards, that is the spring force and the damping force. But the inertial force is acting downwards. So based on that, in the later part, we can equate the force that is acting downwards to be equals to the total forces that is acting upwards. But remember, both all the three components, that means the spring and the dashboard, the force is acting upwards, but the inertial force for the mass is acting downwards. So we must include the negative sign for this. Okay, in the next slide, I will show you that. So here, M represents the mass, the lowercase letter m represents the mass of the suspended spring, but usually that is being neglected. Okay, S is the spring stiffness. Now the uppercase letter M, the uppercase letter M here, it should be the mass, okay, the mass of the object that is hanged on the spring and between the spring and the dashboard. Now S is the stiffness of spring. Usually, this unit measurement for the spring stiffness is Newton per meter. Okay, that is Newton over meter for spring stiffness. Okay, Newton per meter. So mass should be in kg. So X is the displacement of the mass, or the extension of the spring. Okay, and then C is the damping coefficient or the damping force per unit velocity. So for the damping device or for the dashboard, you will have a force that is acting upwards like this. Okay, and the force which is acting upwards here is given as C, the damping coefficient, multiplied by the velocity, x dot. And for the spring also you have a restoring force which is acting upwards, that is given as, the spring stiffness S multiplied by the extension of the spring or the displacement of the mass. And for the mass M here, you will have an inertial force that is this, the mass multiplied by the acceleration. Okay. Now delta is the static deflection of the spring. So based on this, so you can see okay, the oscillation. So I have to use this as manually. Okay, so you can see how the thing will oscillate. Okay, so now the accelerating force or the inertial force acting along the motion of the mass is mx with two dots, that is the acceleration. Damping force or the frictional force on the mass acting in the opposite direction to the motion of the mass, that is the damping force. The C is the damping coefficient, and the x dot here refers to the velocity. Spring force or the restoring force, which is also acting opposite to the motion of the mass. Spring force, stiffness of spring, multiplied by the displacement of the mass. So based on these three forces and second law of motion, so you have mass, the inertial force is equals to the negative damping force and negative spring force. Okay, I hope you understand the equation. Okay, so it is actually written as m, that is the mass, this is the acceleration, is equals to negative damping force minus or negative spring, the restoring force of the spring, Sx. Okay, so or we can write it in differential into the differential form here. The x double dot is actually differentiating the displacement with respect to time twice. Velocity, which is differentiating the displacement with respect to time once. Okay, so when you bring the term on the right hand side over to the left hand side, you will have this equation. Okay, so equals to 0 on the other side. Okay, so if the whole equation you were to divide it by mass, so you will have C over m here, C over m, and the S over m. S over m, that means the spring stiffness divided by the mass of the mass that is attached to the system. Okay, so for example, I can let actually k square be equals to d square x over dt square, and k to the power of 1 as dx over dt, and k to the power of 0 as for x. Okay, A is for the mass, B is for the damping coefficient, and C is for the spring stiffness. In this case, I let it be like that. Okay, as in a form of, as you can see, this is a quadratic equation. So solving quadratic equation, okay, so you have to divide throughout by the A. Okay, and then I have let k square be equals to d square over x over dt square, k to the power of 1 as dx over dt, k to the power of 0 as to become x. And A is to be the mass, B is to be the damping coefficient, and C to be the string stiffness S. So the whole equation from the previous slide Okay, as you can see, okay, if we were to replace the k squared, the b, the a, the k, the c, and the a, you will have this equation here on the next slide. Okay, so the k square is actually your d square x over dt square. Okay, your c over m, and then your k is actually a dx over dt. Then you have s over m, k to the power 0, which is your x actually. Okay, so based on this quadratic form, okay, so in order to determine the roots of k1 and k2, I hope you still remember your quadratic equation, the formula in order to find out the roots. You can use this formula. So based on this formula, you can further manipulate so that you can have this, and then further on, okay, you can break it up in finding out the roots of k1 and k2 in this case. So you can see the whole equation now is in terms of the damping coefficient, the mass, and the spring stiffness. Okay, that's for this section. Thank you very much. Okay, it will be continued because